So today we're going to introduce you guys to probably one of the most important theorems in calculus, the mean value theorem. I would say like the most important one is the fundamental theorem of calculus. That's the one where you take the integral that's equal to the antiderivative subtracted. I'll show it to you. It's in our lesson today again. Actually, we're not going to use it, but I'm going to show it to you. Matter of fact, I'll show you now. It's the one on the bottom. You guys remember that one? Yeah, that's pretty much like a biggie. The other one, I would say that the other one that is mean value theorem. I'm trying to think of another one. Now, we have learned something called the extreme value theorem, intermediate value theorem. You're going to see all of those on your AP exam at one point, I guarantee you. MVT, though, is pretty popular. You're going to see it a lot on your AP exam. So it's a very important one to know. So basically, I'm going to tell you what it is, and then we're going to use it to actually do some problems. So what is it? That's what we're going to start with. Let's go ahead and begin. Let us begin by saying I've got a graph, and I've got one x value here of A and another x value here of B. I'm going to put a point here and another point here, and I'm going to connect my dots with a curve like that. Let's say the y value that goes with the A, f of A, would be right about here, right? And the y value that goes with the B is going to be right about here. That's f of B. And so the coordinates of this point are A, f of A, and B, f of B. The function, I'm assuming, is called f of x, right? So there's that. This is something I would encourage you guys to write down, because it kind of explains what the mean value theorem is. So I can pause for a second if you're still caught up. So I'm going to draw a secant line. Okay, a secant line, as you guys might recall from way back in chapter 1 or unit 1, is a line that connects 2 points on your curve, a straight line, whose slope tells us the what? Average rate of change. I'm going to get your point. Yes. It tells us the average rate of change. Okay? So, what's another word for average? The mean. So, our lesson today is on the mean value theorem. Hey, sir. Cool. Thank you. Appreciate it. Yep. Sorry to interrupt. Appreciate it. Yeah. So, the secant line gives you an average rate of change. This is a curved function, right? So the slope is constantly changing. So the secant line tells you the average velocity, the average rate of change, right? So now let's find the slope of that function. As you guys know, the average rate of change is y2 minus y1 over x2 minus x1. So that would be f of b minus f of a over b minus a, right? That's our average rate of change. So now what I'm going to do is I'm going to ask somebody to come on up here and draw me a tangent line that's parallel to the secant line. Who is so bold? Jillian is so bold. I don't know. Oh, there is, but it's kind of hard to get it just right whenever you're trying to make it. You got to go straight into the board, and don't be afraid to give it a tiny bit of pressure. Oh, yeah, that's not great. It's good enough. I'm not picky. As long as it's got the point, right? So I asked for a tangent line that's parallel to the secant line, right? Thank you. And I agree. I think that's good. So tangent line, you got to remember, is a line that touches your curve at one point And what does a tangent line tell you?
At one point.
Now it hits it at one point. Now that gives us a new value, doesn't it? That gives us a new x value. We'll call it c. Right? And so this point up here we can call c f of c. It gives us a new point. Now, so the slope, what's the slope of the tangent line at that point? How would I write that? No, that was the first one, the average. There you go. Instantaneous rate of change is a derivative. So it's f prime of c. Okay? Now I told you to draw one that is parallel to the secant line, right? And what do we know about parallel lines? They got the same slope, which means guess what?
They're the same.
Okay. That is kind of what the mean value theorem is. The mean value theorem is a theorem that promises us that there is some point somewhere along this curve where you have an instantaneous rate of change that is exactly the same as the function's average rate of change. Okay? Or you could say it another way. There is a tangent line that's parallel to a secant line, right? So that's what it promises us. It promises us that there is some x value between the two endpoints such that the derivative is equal to the average. Yeah.
Where'd your fish go?
My fish is at home. I had to take him home over the break because they were turning off all the power. He's not dead. He's okay. My daughter's taking care of him currently. All right. Now, I'm gonna throw a few new facts in there. What if I were to do that?
I wouldn't like it.
What? Now my function is no longer what?
Continue.
Continuous. And if it's not continuous, it's not
Differential.
differentiable, which means there is no instantaneous rate of change at that point, which means there is no point where they're the same. So one of the rules for the mean value theorem is that it has to be differentiable. There can't be gaps or jumps in it. Okay? It has to be differentiable. The other one is, since you're trying to plug in these endpoints, right? You have to be able to plug your endpoints into your function. If they're not actually on the function, if it's an open interval, for instance, you can't do it. So that's pretty much it. Now, the mean value theorem is an existence theorem. It's like the IVT. The IVT, if you guys don't remember, that's the one that says if you have a point up here and a point down here, then there's got to be a point somewhere in the middle, right? Then there's the EVT, which we learned last time, which says that if it's continuous, you've got a max and a min. But none of these theorems tell you what they are, right? They just tell you that they are, correct? Not only do they not tell you what they are, they also don't tell you how many there are. Same thing here. The mean value theorem guarantees that there is at least some point where the slope is the same, but it doesn't tell you if there's one or two or three. Maybe there's a bunch. I'll give you an example of that. Suppose you had this. You don't need to draw this part. But same 2 points, let's say, right? But what if your graph went like this? Well, now there's 2 places where you could have a slope that is parallel, right? So you would have 2 answers at that point, right? So it doesn't really guarantee that you're going to end up with, all right, want to talk about it? I'm not, you guys are, whatever. I don't care. Do what you want.
You just triggered Mr. Bailey.
You're childish. Right. So, I'm done.
I'm so glad. I was the only one laughing about that last period.
Childish.
I knew what you were giggling about. I didn't
Yeah.
if I make a
Yeah.
big deal about it in your class, I think the roof
And-
would explode.
Yeah.
So I did definitely say nothing there. All right. So I guess I should have picked a different shape.
That's nice.
Okay. Here we go. Here's your mean value theorem. Disappointed in you. Disappointed. All right. I'm going to tell your seminary class in the morning. You go there and tell them. All right. So it's got to be continuous, no holes or gaps, and it has to be differentiable. The derivative has to exist everywhere. Otherwise, the one place where it doesn't exist might be that one spot where it would have worked. So it has to be continuous and differentiable. No cusps, no gaps. But if that's the case, then there is some place where the instantaneous rate of change equals the average rate of change. Okay? Now, why do we care about it? You know, honestly, I haven't seen too many applications that would make you guys feel like, oh, that is kind of cool, other than what I just showed you. Now, mathematicians, though, find this theorem very useful. Do you guys remember this one here?
Yeah.
That's the limit definition of a derivative, right? But don't you, if I cover up that limit, isn't that the same thing? Right? So, I mean, there's one thing, right? Now, another thing, this one's not as obvious, but if I take this mean value theorem, which is, this is very ghetto math, so if there's any official math people that are going to watch my video, they would, like, judge me for what I'm about ready to do, but that's okay. It is somewhat true. It makes the point. So, right, we have this as our mean value theorem. If you multiply both sides by b minus a, this goes away, and this is b minus a, right? B minus a is the difference between your two x's, right? That's your delta x. Delta x is dx. So if I just change this to a dx, that's where probably one of the most important theorems in calculus even come from. Do you see it there? This is f prime. Remember the capital F is the antiderivative? And I'm writing a little bit different up here. The point is that this is the antiderivative of this. This is the antiderivative of this. So anyway, both of those very important theorems come from, they use the MVT to guarantee that that point exists so they can derive that theorem. So without the MVT, you lose like the cores of calculus. So it's actually a very important theorem. But you guys aren't going to be doing any proofs like that of any kind, so you don't have to worry about it, but I'm just telling you why they care so much about it. All right, so now we're going to actually do what you guys will be asked to do with the MVT. So go ahead and write down your directions there in the problem. Oh, actually, you don't have to. My last class made this mistake. It's on there. I printed it. I titled it differently, but I put it on there. It's called Guided Practice 1.
Hey, Mr. Fan, it's your example.
I'm not talking.
This is a helicopter.
It does look like a helicopter. All right. So they put the same one in the book that I drew. Then I'm not creepy. It's just how it is. All right. So yeah, it's just for you. I doubt mistype. All right. If the MVT can be applied to the given function, notice it says if, find all the values of C in the interval such that what we just talked about is true, that the instantaneous rate of change is equal to the average. So we want to know where is the instantaneous rate of change exactly the same as the average. Huh? Good point. So when you're proving that the MVT applies, it has to be continuous on the closed interval. The differentiable just needs to be open. So we only care about open for this case. If the MVT cannot be applied, then explain why. Okay, now let's go ahead and begin. Can we use the MVT? That's the first thing we have to do is establish that fact. Step 1. Can we use the MVT? And there's two things that we have to establish. we need to establish that it is in fact continuous on what interval? 1, 4. And we also need to establish that it's differentiable on the open interval 1, 4. And whether it's open or closed for us, mathematically, what we're going to do is not going to make any difference, but that's just how they define it. The reason why it's continuous on the closed interval is because you have to have the endpoints, because isn't that how you get your slope, right? So you need those included. But for the derivative, since it's somewhere inside, you don't need it to be on the endpoints. So anyway, there we go. So can we use it? Well, this is where you take out your notebooks and you flip back to chapter 3 and you find that long list of functions and where they're continuous and where they're not. But we've been doing these so much at this point, I think you guys probably know what kind of function is this. And polynomials are continuous everywhere. So we're good. Since it's a polynomial, it's continuous everywhere. I'll go ahead and write that. Since it's a polynomial. Now, how can you, this is a big question, how can you tell if it's differentiable on the interval? Well, you have to find the derivative. So let's do that. What is f prime of x? Now take a look at 2x minus 3. Are there any x values in there that would not exist? No, because once again, that's a linear function, right? Which is really just another type of polynomial. So really the way you tell if it's differentiable or not is the same way you tell if it's continuous. You just look, but the difference is that you look at the derivative instead of the original. So since the derivative is continuous, that means the original is differentiable. Does that make sense? All right, so check. Since f prime is continuous, I guess we could say is a polynomial. So it's good. We're done. That means that somewhere, and I'm going to go ahead and bring up the picture now. Here's the graph that I'm concerned with. There's my graph. There's no holes or gaps because we've said it's continuous. There's no cusps or either because we know it's differentiable. So we have a nice smooth curve. And we know that the average rate of change is somewhere from here to here. And it makes sense that obviously somewhere along that curve I could draw a tangent line that's parallel to that secant line and find that slope, right? So that's the gist of it. So let's go ahead and do that. So after you've said that yes, the MVT applies, that point actually does exist, you're ready to go ahead and begin. See if you guys can figure out what goes in these blanks. One of them probably is a little tricky. You know? Go for it. What goes here?
4.
I agree, because it's A and B are the endpoints, right? So 4 goes there and there. How about the other spot? Right next to it.
1.
Yeah. So the endpoints go in that one. Now this is the tricky one. Do you know what goes here? C. Now X isn't wrong, I guess, but they might. I don't know. It depends how grumpy your grader would be if you're on an AP test. They might actually think, no, it says C, so you have to write C. They might. All right, so f prime is C, right? Now let's go ahead and do this. So what is f of 4?
6.
That was fast.
Yeah.
It's on the graph.
Oh, nice. What's f of 1?
0.
Now, how would you usually find it?
Plug it in.
By plugging it in, right? So you plug 4 into your original function, you plug 1 into your original function, you got that. Now here's what's confusing about that, because you also have a derivative, right? Last class I had a lot of people plugging it into the derivative, so you got to watch out what you're plugging it into. These are regular f's here. Now the one over here on the left, that is a derivative. Okay, now I don't have a number here though. But we do know our derivative. What was our derivative? We wrote it down earlier. 2x minus 3. But instead of 2x minus 3, what am I going to write? 2c minus 3. Then we solve for c. It's pretty simple after that. So 2c minus 3 is equal to 2. If you add 3 and divide by 2, you'll end up with 5/2 or 2.5. Now that answer makes sense because if you come over here to your graph, we had our secant line, right? 2.5 is right here, so if I go up and put a dot and draw a tangent line there, that's about parallel to the other one. So we found the point at which the instantaneous rate of change is equal to the average rate of change. Okay? All right. All right. Guided practice. So this one I'm going to use my cards. I'm going to call on you and ask you to kind of help me out with it. So, guys ready? Guided practice. All right, so Michael, what's the first thing that I need to do?
You have to find C to the
That's right. We have to make sure that we can actually, we have to be sure that point actually exists. In other words, can we do the MVT? So, Jocelyn, if I want to use the MVT, what do I have to check for? Good. So, is it continuous? So, let's ask Jacqueline, is it continuous? Yes. Why is it continuous? Good. So since I didn't call this f of x, I'm going to do that now. Since f of x is a polynomial, it is continuous on the interval -1 to 1. All right. Wendy, what do I need to do next? And by the way, I wasn't this thorough on my last one, but if you were doing an FRQ, that I think they would want you to be this thorough with your explanation. Like, since it's a polynomial, it is continuous on the interval. Okay. So is it differentiable, right? Good. So I asked Wendy what was next, and she said differentiable. She's right. Now, how can we tell if it's differentiable? Kwaku, how can we tell if it's differentiable? What do I need to do that? We will need to look at the chart. Good. But this time we're going to look at the chart for the what instead, Kirsten? Okay. Somebody know? Huh? You're going to look at the derivative. So we need to find our derivative. All right, so let's find the derivative. I'll write it up here. The derivative is 6x to the 5th. So we're going to look at the chart for that. Francisco, is this continuous on the interval?
Yes.
Yeah, because why? It's still a polynomial, right? So, and since f prime of x is a polynomial, it is continuous on that interval, and it is differentiable. On -1, 1. Yes. I mean, I don't think they would take off points. Matter of fact, they have explicitly told me they don't. At my last meeting, they say they don't care about that, but I think that's a good insight, so I'm going to go ahead and say yes to that. That's a good idea. All right. Now, since f of x is a polynomial, it's continuous and differentiable on the interval. Therefore, there is some C such that f prime of C good. Now what is my B and A?
The 1 and then
Good. Is that right?
yes.
Okay.
Should we
Oh yeah. Sorry. Yeah, so I didn't do this with Nick's class, so sorry, Nick. I didn't do what I'm doing here. I'm being very thorough in how I write it because this is how you'd write it on like an FRQ. Sorry. We'll figure it out. Okay, so let's go ahead and finish it up. Why don't you guys take it from here and see if you can find C for me. I'll pause the video and give you a minute to do now. And what did you get?
1.
Okay, got you. So he plugged in 1 here and he got 1. Minus, what'd you get for f of negative 1? And then on the bottom? And did your voice get deeper? That was really weird. I heard 1. I heard 1. All right. What goes over here? Which is? Kind of. Yeah. Okay. And what does Jillian? What does this equal? Hmm. Yes. And therefore C equals. I'm not. You guys could divide by 5 and take the 5th root if you want to, but it's just going to be 0. All right. So there it is. That's the place where the instantaneous rate of change is equivalent to the average rate of change. All right. So another one, but this one you guys can do from beginning to end on your own. There you go. In the interest of time, I'm not going to write, but I will speak the beginning. The beginning is, since it's a polynomial, it is continuous and differentiable on this interval. Matter of fact, guess what? If you want to save yourself some time on the AP exam, you could just say, since it's differentiable. Why do you only have to say differentiable? Because that makes it continuous. So you can actually just say it's differentiable and be set, just so you know. But it is a polynomial, therefore it's differentiable, therefore it's continuous, therefore there has to be some point along the curve where the instantaneous rate of change is equal to this. In other words, there has to be some value of C such that f prime of C is equal to f of 1, 0, 1, 0. So I know you guys aren't done yet. That's okay. We're not going to stop you just yet, but I do want you guys to catch me up. So Heather, what's f of 1? Good. And Eric, what did you get for f of 0? Good. And this is over 1. And I shall ask Jocelyn Lopez, what am I going to put over here? Which is?
3c squared minus 6c plus 9.
Good. And so we have 3c squared minus 6c plus 9. And this is where most people are getting, and then they kind of don't know what to do at this point. So what kind of a function is this? It's a quadratic, which is a polynomial, but it's a quadratic. And when you have quadratics, you need it to equal what?
0.
You need it to equal 0. So I'm going to pull this 7 over here. And it would be really not. What's your guys' first instinct when you see this on how to solve it? Yeah, factoring, right? I'll save the trouble. It doesn't work. You can't factor this. The box method or wherever it fails, and the GCF fails. So what's the other way to solve it? Oh, I didn't fix that. What's the other way? This is supposed to be 2. Sorry about that. The quadratic formula. So that's how you're going to solve it.
It's 3 plus square root 3 over 3 and 3 minus square root.
Very good. Very good. You're right. That is correct. I'll show you, but here it is.
Try to figure it out.
Oops. So there are two places. In other words, there's two tangent lines on that curve that are parallel to the secant. Because we have 3 plus the square root of 3 over 3 and 3 minus the square root of 3 over 3. Okay, I can show you on the board. We're going to do a couple more, but we're not going. These problems we're not actually going to do, and here's why. The reason we're not going to do them is because on all of these, the MGT does not apply. And I just want you guys to have a few examples in your notes where you see cases where it fails, and I want you to see how to write it. Then I would really like to, but I don't think we're going to get to it, but I'm going to try to get to that word problem. So it depends on how quickly we can move through these. If not, I'll just add it into the notes after class today. If you guys want to look at it to help you with your homework, you're welcome to. What kind of a function are we looking at here? Rational. And rationals do have discontinuities. It's on that sheet. Rational functions do have discontinuities. Where is this one's discontinuity at? It's at 1, because the denominator cannot equal 0, right? X minus 1 cannot equal 0, which means that x cannot equal 1. So we have a discontinuity at 1. Is 1 in this interval? Yes. Now, if it wasn't, then we don't have a problem. We could do the MVT and actually do this problem. But since 1 is actually on the interval, it may be the case that the one place where that instantaneous rate of change would match the average is right where that discontinuity is, so we can't be sure that that value of C exists. So we're going to say, explain why the MVT does not apply. We're going to say because the function is not continuous and therefore not differentiable at x equals 1. And if you wanted to be even more specific, you could say, because it's not continuous at x equals 1, and 1 is on the interval that we care about. But I don't think that would be necessary on the P exam, but for notes purposes, it might be nice to see that later. Because you guys caught one, I think Jonathan caught it last class, where I was doing the EVT, right? And I found an extra critical value, but it wasn't on the interval we cared about, so it actually shouldn't have been considered, right? So you do have to pay attention to those intervals. All right, can I proceed? All right, let's do another one where the MVT fails. Don't write the directions again. It's the same, just call this number 2 under the same example or whatever, and write that down. All right, so what kind of a function are we looking at here? Absolute values. Are they continuous? They are. They don't have any holes, gaps, or jumps, so check, we're good. Now, their derivatives. Is it differentiable? It's not, because what do they have? They've got cusps, right? So we know there's going to be a cusp somewhere. Does anybody know where? 5. Now, this would not satisfy as our answer. I'm just putting that up there for notes. There's a cusp at 5. How do we know that? Because the way you find the cusp, that's where the two pieces connect when you change it to a piecewise function. You take the part inside and you set it equal to 0. And that's where they connect, right? So that's how we know it's at 5. It's not just because there's a 5 here. It's because we set that whole thing to the 0 and solve. Okay, so here's our official answer. We're going to say, because the function, by the way, I'm really tempted to write it's, because it's not, you can't do that. You don't use the word it on the exam. You have to say the word. Because the function is not differentiable at x equals 5. That is the answer. That was just for your notes, so you know why it's not. Mhm. Pi over 2. Mhm. Mhm. Well, yeah, I mean, yeah. You could have just stopped here, right, and done that by looking at the chart. Yeah, so you just want to find Windows cosine. All right, let's do one more. One more. One more. This one is just to frustrate you. This is just to remind you that trig matters.
All trig matters.
It's like that annoying thing that just keeps popping up over and over again. It's not going to go away. Yep. All right. So, is it continuous? Crickets, right? We don't know. So, look at your sheets. Look at your sheets, right? Now, I don't know if you have them in front of you now, but if you look at those function sheets that I gave you, cosine is continuous everywhere. Tangent has discontinuities at pi over 2, 3 pi over 2, ad infinitum. Okay, just keeps going on and on. So, is pi over 2 or 3 pi over 2 on this interval? You have to know that, right? So, 0's over here, pi's over here on the unit circle. Pi over 2 is up here. So, is it in between them? Yes. So, the answer to this is because the function is not continuous at x equals pi over 2. So you gotta watch out for those kinds of things. Now, but remember, I think one of your homework problems tonight has a trig in there. It's sine, but sine is like cosine. It's continuous everywhere. So I didn't get to the word problem, but I will add it to the notes. So I'll pause my video, and whenever it's quiet in here, I'll do it real quick. If you guys want to watch it, help with number 60, you're more than welcome to. So here's that promised word problem. It says, a plane begins its takeoff at 2 p.m. on a 2,500-mile flight. After 6.25 hours, the plane arrives at its destination. Explain how we can be sure that at some point in the flight, the airplane was going exactly 400 miles per hour. Now, I think the one that I printed on your worksheet that I handed out to you guys, your notes today, is worded differently. So I changed it a little bit. And if you want to make that adjustment on your notes for future reference, you can. But anyway, I'll go ahead and answer this question. Now, it's obvious maybe how we might approach this today because we're talking about the mean value theorem. But, you know, if I were to throw this problem at you out of the blue on some final test or something, it's kind of difficult to recognize that this is actually an MVT problem. And the reason why it's an MVT problem is because they're asking us how we can be sure that at some point, in other words, we're not saying that they're what the point is, we're just sure that that point exists. So right away, that little sentence there, that a point exists, that tells us that we're using either the MVT, the IVT, or the EVT. Now the EVT talks about mins and maxes. The IVT just promises that there's some point in between two other points. The MVT talks about average rates of change being equal to instantaneous rates of change. So how do we know which of these three it is? Well, if you read on, it gives you another clue. It says 400 miles per hour. Now that is a rate. So we're not talking about mins and maxes. We're not talking about a number in the middle of two other numbers. We're talking about an average rate of change, which tells you right there, we're talking about the mean value theorem. So there are some clues in this word problem that can suggest that you would apply the mean value theorem to this particular problem. So what we have is we have an airplane. So I'll draw a little ghetto airplane here. And it's going to take off, stay in the air for a while, and then land, right? So that path that is traveling, that's our function, right? We know that it's traveled a total distance of 2,500 miles in a total time of 6.25 hours. Okay? So how would I apply the MVT to this? Well, here we go. First of all, is the airplane going to just stop existing at any point in its path? No. So that airplane constantly exists, which means that it's continuous. And it's also differentiable. Now that one's a little bit harder to see, but let me explain why. There's two things that would cause something to not be differentiable. One is that it's not continuous, and we've already established that it is continuous. The other one is a cusp. At no point in a flight is an airplane going to suddenly just poof, drop down. It doesn't do that. Even if it crashed, ran out of gas or had a malfunction, it's going to smoothly drop down. So you're not going to have a cusp. That's impossible. So we can say that since the flight path is continuous and differentiable, that means there must exist some value. I'm going to use t instead of c for this because we're talking about time. There must exist some time at which the instantaneous rate of change of this airplane, which is the derivative of the function, is equal to its average rate of change. Now, what is the average rate of change? Well, we know the total distance. It went a total distance of 2,500 miles. That's the difference in the y values. And you guys know that speed is distance over time, right? And the time is 6.25. And guess what that just so happens to equal? 400. So, since the flight path is continuous and differentiable, there must exist some time at which the instantaneous rate of change is exactly 400 miles per hour. And that's what the question was asking. It said, how can we be sure that at some point in the flight, the airplane was going exactly 400 miles per hour? Well, we can be sure of that because it's continuous and differentiable, and therefore the mean value theorem guarantees that the instantaneous rate of change at some point in time in that flight had to equal the average rate of change of that flight. So there you go. That's your one word problem application there. Okay, so that's that. We'll see you guys in class next Tuesday.